All right, so where are we in the schedule? All right, so today is Thursday, August 27th. So we're over here, Thursday, August 27th. We're going to finish chapter 0. I'm actually going to start with 0.13, and I'm going to wrap back to a very quick review of 0.11 and 0.12, but I expect you to review those on your own, solving equations and inequalities. I'm going to briskly review them here, but I expect you to review those on your own. All right, so we'll finish chapter 0 today. You can do all the homework for chapter 0 by next week. On Tuesday, I'll get a head start on chapter 1, although that will not be due later in the week. I can start discussing some homework with you folks if you have questions, and we'll have a larger homework session 1 week from now on Thursday, September 3rd, and I'll continue with chapter 1. Your homework due date will be Friday, September 4th for chapter 0 only. Okay, no chapter 1 is due on Friday, although I do encourage you to keep up. Remember, there's also the Alex extra credit stuff. You may as well do it now while you're learning it, right? Okay, any questions about the schedule? All right, let me see here. Let's see. Okay, answering chat. Okay, any questions? Any questions? Whoops, wrong person. All right, anyone else in the chat? Anyone else in the chat or anything? Okay, so let's start. We're going to start with 0.13. I'm going to wrap back to 0.11 and 0.12 later. We're going to start with 0.13. Okay, let's do it.
Hi, everyone. We're going to section 0.13 on the Cartesian plane and circles. Basically, it's this classic XY plane over here. Cartesian is named after René Descartes, the founder of analytic geometry. Descartes, according to the story, was thrown off of his horse and he was medicated and put in bed. So while he was in bed, Descartes, well, he was also someone who tried to prove the existence of God one time, but while he was medicated in bed, he looked up at the ceiling and he saw a fly up around the ceiling. And he said, dude, I noticed that I can locate the position of this fly if I figure out its distance from this wall and that wall and the ceiling. And that, ladies and gentlemen, is the origin of modern analytic geometry. Descartes, medicated and delusional in his bed. Anyway, what do we have here? We have a horizontal line called the x-axis, which is a real number line, and we have a vertical line called the y-axis, which is also a real number line. So we have these two perpendicular real number lines, and they intersect at a magical point called the origin, which we'll denote with the letter O. Now, each point in the plane can be said to have an x-coordinate and a y-coordinate. So, for example, the origin corresponds to the ordered pair 0, 0. The red point here corresponds to the point 2, 3, surrounded by parentheses. The 2 is the x-coordinate of the point. The 3 is the y-coordinate of the point. Because this point is 2 units to the right of the y-axis, so that's the x-coordinate of this point, and this point is 3 units above the x-axis. So its y-coordinate is 3 units. It's an ordered pair because 2, 3 is different from 3, 2. That ordered pair corresponds to a different point over here. All right. Now, if we have 2 distinct points in the Cartesian plane, what can we try to figure out? So let's say that we have these two generic points here, x sub 1 comma y sub 1, and x sub 2 comma y sub 2, where these are all real coordinates. Well, we might want to ask two questions. First question, what is the distance between these 2 points, denoted by this letter D? In other words, what is the length of the line segment that connects these 2 points as endpoints? A second question could be, what point lies at the center of this line segment? What is the midpoint of these 2 points on this line segment? It's like a pit stop on this highway. All right. So the distance between the 2 points, denoted by D, is given by basically the Pythagorean theorem, which we'll talk about later on in Trig, chapter 4. The distance is given by the square root of the difference in the x-coordinates squared plus the difference in the y-coordinates squared. Now often, we denote the difference in x-coordinates by delta x. The triangle means capital delta. It means change in. The capital Greek letter delta means change in. And likewise, y sub 2 minus y sub 1 can be thought of as delta y, the change in y. And actually, it doesn't matter if it goes x sub 2 minus x sub 1 or vice versa. Same with these y guys over here. Because remember, if you were to switch these two guys, you would end up with the opposite, but opposites have the same square. So it doesn't matter if you switch these or not. In our picture, it would make sense that x sub 2 minus x sub 1 would be the non-negative quantity, that's delta x here, and y sub 2 minus y sub 1 would be this non-negative quantity here, delta y. Because the second point is northeast of the first point. Bear in mind that delta x and delta y could be negative, and these squares here ultimately don't care. So the distance is given by the square root of the difference in x's squared, we don't care which order, plus the difference in y's squared, we don't care which order. Again, we don't care which order. It could be x sub 2 minus x sub 1 over here, or x sub 1 minus x sub 2 over here. It does not matter. Same with the y's. And again, this comes from the Pythagorean theorem. How do we get the midpoint? Well, come on. How do we get the x-coordinate and the y-coordinate of the midpoint? To get the x-coordinate, we take the 2 x-coordinates of the endpoints and do what with them? Take their average. How do you take the average of 2 numbers? You add them up and divide by 2. So the x-coordinate of the midpoint is obtained by x sub 1 plus x sub 2 all divided by 2. That's how you take the average of 2 real numbers. Likewise, to get the y-coordinates, y sub 1 and y sub 2, to get the y-coordinate of the midpoint, you take the average of the 2 y-coordinates. You add them up and divide by 2, just like with the x-coordinates. Remember to put parentheses to indicate that we have an ordered pair. Hi everyone, let's do an example. So here, we have the point negative 2, comma 1. And here we have the point 3, comma 3 in the Cartesian xy plane. Now let's call negative 2 x sub 1, and let's call 3 x sub 2. Or we could switch these, that's perfectly okay. However, if you call negative 2 x sub 1, then 1 here better be y sub 1, and then the 3 over here better be y sub 2. So let's plug into the distance formula to find the distance between these 2 points, the length of this connecting line segment between the 2 endpoints. The distance equals the square root of delta x, the difference in x's. 3 minus negative 2. Or you could go vice versa. That difference is squared. Don't forget the square. Plus the difference in y's, y2 minus y1, that's 3 minus 1, or vice versa, all squared. The end result is root 29, and you should put a unit here, meters. Assume that the x and y axes are scaled in meters, unless I say otherwise. So the distance between these 2 points, or the length of this line segment, will be root 29 meters. Between what and what? Between 5 and 6 meters, right? Because 5 is root 25 and 6 is root 36. So this would be 5 point blah, blah, blah meters. Now, what are the coordinates of this midpoint, M? What are the coordinates of the midpoint? To get the coordinates of the midpoint, we basically average the coordinates of the endpoints. So to get the x-coordinate of the midpoint, to get the x-coordinate of the midpoint, we take the average of the x-coordinates of the endpoint. To get the y-coordinate of the midpoint, we take the average of the y-coordinates of the endpoints. All right, so the x-coordinates of the endpoints are negative 2 and 3. Add them up, divide by 2. We're averaging them. The average of negative 2 and 3 is 1/2. It's okay that 1/2 is not an integer. Not all real numbers have to be integers. 1/2 is perfectly good as a real coordinate. You're spoiled with integers back in your algebra classes. Now, what about the y-coordinate of the midpoint? Well, we're going to average 1 and 3. Basically, the midpoint between 1 and 3 is 2, the average. So the coordinates of the midpoint will be given by 1/2 comma 2, and don't forget to surround those by the parentheses to indicate an ordered pair. 1/2 is the x-coordinate, 2 is the y-coordinate, which makes sense. We're in quadrant 1, where both x and y coordinates are positive. Next up, we're going to talk about graphs of equations and circles.
Any questions about the distance formula, the Cartesian plane, or midpoints? Any questions? Any questions? All right, let's go on to graphs and circles. Feel free to chat.
Hi, everyone. Let's talk about the graph of an equation in general, and then go on to circles, some very basic graphs. The basic principle of graphing. This may be obvious to some of you, but actually it's a lot deeper than you might think. The graph of an equation consists of all points whose coordinates satisfy the equation. The graph of an equation consists of all points whose coordinates satisfy the equation. The points correspond to solutions of the equation. I might call them solution points. So if I graph something in the Cartesian plane, then all the points, all the solution points on this graph will satisfy the equation of the graph, which will be ya equals ya. Okay? So that's the idea, the basic principle of graphing. Some of you might say, oh, that's obvious. But here's the deal. Later on, when we deal with polar coordinates in this class, or in 3 dimensions, if we're dealing with cylindrical or spherical coordinates, or for that matter, Cartesian coordinates in 3 dimensions, the basic principle of graphing will come in very, very handy. What's the graph of an equation? It consists of all points whose coordinates satisfy the equation. So if I ask you to graph an equation, I want you to plot all these solution points whose coordinates satisfy that equation. All right. Now, some very basic graphs are circles. And without even talking about x and y, what is the locus definition of a circle? What is a purely geometric definition of a circle? This is called the locus definition of the circle, without even going to x and y. All right, we begin with a fixed point, which is going to be the what of the circle? The center. And we want all points that are the same distance from the center. And I'm going to call that distance r. Why? Because r is going to be the what of the circle. I'll do this in blue. Do some blue. R is going to be the what of the circle. R is going to be the radius of the circle. It's the distance between each point on the circle and this fixed point called the center. Bear in mind that twice the radius is called the diameter. Twice the radius is called the diameter. Now be careful, because the letter D might refer to specifically the diameter, or could represent a more generic distance. So be careful about the letter D. Know for sure what it means. Does it mean distance? Does it mean specifically a diameter? What is it? By the way, you can define a diameter as the length of the longest chord that can go through a circle. In fact, a diameter can be defined as the longest chord that goes through a circle. A chord is a line segment that connects 2 points on the circle as endpoints. 2 distinct endpoints. The diameter is the longest such chord that goes through a circle, and it has to go through the center. Okay, so that's the locus definition of a circle. Now, how can we get an equation of a circle in the xy plane? So in particular, if I want to consider the equation of a circle whose center is at the origin, 0, 0, in the xy plane, and whose radius is r for some positive length r. Remember, a radius has to be positive by definition. The radius is the distance between any point on the circle and the center. All right. Well, if I take a generic point, xy, on the circle, first of all, how can I represent the distance between this generic point xy and the origin 0, 0? I can use the distance formula. And from the distance formula, what do we get? What's the distance between x, y, and 0, 0? It's going to be the square root of x minus 0, all squared, plus y minus 0, all squared. But of course, we don't have to have the minus zeros. So we can just say that the distance here, r, the radius, is given by the square root of x squared plus y squared. X squared plus y squared is the desired radius, the distance between a point xy on the circle and the origin 0, 0.
The square root of that.
So far, I have this as a proposed equation for the circle. I'll turn this around. I have the square root of x squared plus y squared equals r. You could say that that's an equation that represents this circle of radius r centered at the origin. But we don't like the square root over here, so we're going to square both sides. I'll do this. On your homework and notes, try to be cleaner, but I'll just do this for now. Well, I'm going to square both sides. The square of r is r squared. All right. Now, when you take the square of a square root guy, what happens? You get the radicand. assuming that the radicand is non-negative. But the thing is, x squared plus y squared is guaranteed to be non-negative if x and y are real. If x is real, x squared is never negative. If y is real, y squared is never negative, and their sum can never be negative. That's good to know. X squared plus y squared can never be negative if x and y are real. But anyway, the square of the square root of x squared plus y squared, that's going to leave plain old x squared plus y squared, the radicand, equals r squared. Normally, when you square both sides of an equation, you have to do some checking. We're going to be okay here, in part because of this, the fact that we know the radicand is non-negative. So the standard form for an equation of a circle like this, that has radius r and whose center is at the origin, the equation we use is x squared plus y squared equals r squared, where x squared plus y squared is the squared distance between x, y, and 0, 0. It's the square of the radius. So all the points on the circle, here have the property that their squared distance from the origin, x squared plus y squared, this is the squared distance from the origin, is going to be r squared, the square of the desired radius. X squared plus y squared equals r squared. That is, over here, x squared plus y squared equals r squared. That is, I need to write nicer ovals and circles. X squared plus y squared equals r squared is the standard form of the equation of a circle in the xy plane with center 0, 0, the origin, and radius r, where the radius r is positive. Okay, here's a much cleaner picture. This is the graph of x squared plus y squared equals r squared. According to the basic principle of graphing, this is the graph of this equation. The graph of an equation consists of all solution points x, y, whose coordinates satisfy this equation. This includes, for example, r, 0, where x equals r and y equals 0. Consider this equation, x squared plus y squared equals 9. Well, that's going to be a circle. The graph of this equation will be a circle with center at 0, 0, and the radius is not 9. 9 is r squared, remember. R squared is 9, so the radius r is 3. I know that 9 has two square roots, 3 and -3, but the radius is the non-negative root. Right, 3 meters, you could say. So here's the graph of the equation x squared plus y squared equals 9. How many points lie on this circle? How many solution points are there for this equation? Infinitely many. Infinitely many. But 4 of them are very obvious. 3, 0, 0, 3, -3, 0, and 0, -3. Those are the 4 most obvious ones. 3, 0 is a solution point. The point lies on the graph because 3 squared plus 0 squared equals 9. So the coordinates of the point will satisfy the equation. But it's not the only one. And these 4 compass points are not the only points that satisfy the equation. Consider this point over here. The point, well, how about over here? The point root 7, root 2. The point root 7, root 2. Is this a solution point? Well, do the coordinates satisfy this equation? X equals root 7. That's squared, plus y equals root 2. That's squared. Does that equal 9? Does that equal 9? Well, the square of root 7 is 7, plus the square of root 2 is 2. Yes, that does equal 9. 9 equals 9. That does check out. So root 7, root 2 is a solution point for the circle And it's a solution for this equation, where x is root 7 and y is root 2, this ordered pair. Don't discriminate against this point just because it has non-integer coefficients. Yes, the coordinates are irrational, but they are real. They do count. This circle has infinitely many solution points. And there are infinitely many distinct ordered pairs that satisfy this equation. By distinct, I mean different. Next up, what happens if we translate the circle so the center moves from 0, 0 to some other point, h, k? How do you translate a circle? Next time.
Any questions before we move on? Any questions? All right, feel free to chat. Let's move on.
Hi, everyone. How do we get an equation for a circle in the xy plane with center h, k, not necessarily the origin, and radius r? We want all points x, y that have distance r away from this center, h, k. So what do we want here? We want all points x, y that satisfy the following equation in principle, where the distance between x, y and h, k is equal to r, the radius. I want all points x, y that satisfy this property. All points whose distance from this center point will be r. Well, what is the distance between x, y, and hk? That's given by the distance formula. The square root of x minus h all squared plus the quantity y minus k, the difference in the y coordinates, all squared. Make sure this all goes into the radical. We need that to equal r. We know that the sum of squares in here is non-negative. Let's square both sides and we get, well, it's right here. Remove the radical on the left. The square of x minus h plus the square of y minus k equals the square of r. This is the standard form for an equation of a circle whose center is at h, k and whose radius is r. I say standard form because, well, here's another equation for the circle, but this is our favorite equation for that circle. All right, so for example, again, we want the circle to consist of all points x, y whose square distance from hk is r squared. The distance has to be r, the squared distance has to be r squared. Example, find an equation of the circle, the standard form for an equation of the circle in the xy plane with center at -2, 1. So this here is going to be h, k, and radius 3. That's going to be our value for r. Let's assume that distances are measured in meters, but that won't come up in our equation. Well, let's apply this formula. And we get, right, by following the formula, we get x minus -2 all squared. Remember, you need grouping symbols around a negative number to make sure here that the minus signs here don't come close to each other. These are sort of like very competitive alpha males or something. You can't have them right next to each other. You have to separate them out using grouping symbols. All right, so we have the square of x minus -2, right, plus the square of y minus 1 equals the square of 3. This is in standard form, but we usually write x minus -2 as x plus 2. So the square of x plus 2 plus the square of y minus 1 equals 9. So either of these would serve as standard form for the equation of the desired circle. Now, if I were to give you either of these equations, and if I were to quickly ask you, what are the center and the radius? Well, for the radius, make sure you remember that the radius is not 9 here. 9 is r squared. R itself is just 3. So do remember that. R itself is just 3, or 3 meters. To read off the center here, here's the trick. The center is -2, 1. The center makes the left-hand side equal to 0. So when you want to find the center of this circle, you're asking yourself, what values for x and y will make the left side equal to 0? The idea is that the center has a square distance of 0 from itself. X equals -2, y equals 1, that makes the left side equal to 0. Remember, folks, the center of a circle is not itself a point on the circle. So the center will make the left-hand side equal to 0, not 9, or r squared. The center of a circle is not technically a point on the circle, but we often like to indicate the center when we're drawing a circle. Okay, so let's compare the two circles we've just seen. This is called a translation. When we go from this equation in black to this equation in red, we're translating the corresponding graph. We're translating the circle. We're talking about translations in general in chapter 1. And yes, it will involve, in general, substituting x with x plus 2 if you want to move the shape to the left by 2 units. And we're going to substitute y with y minus 1 if you want to translate up by 1 unit. Those general principles will apply in chapter 1 for more general graphs. So here is an early example of a translation. Next up, how do we make an equation like this look something like this? Put it in standard form. Next time.
Any questions before we go on, before we go to some intense algebra? Any questions so far? All right, let's proceed with the algebra.
Hi, everyone. How do we get an equation of a circle in this form to look like our nice standard form up here, where we can clearly identify the center and the radius? All right. Now, first of all, note that we have 2 leading coefficients on the left side. We have the 4 as the coefficient of x squared and 4 as the coefficient of y squared. And notice that these terms are on the same side. If these were different numbers, then we probably would not have a circle, would we? So notice that we have a common leading coefficient for x squared and y squared, 4. So we're going to divide both sides of this equation by 4. Remember that 0 divided by 4 is 0, not undefined. If you have no candy for 4 kids, you have 4 crying kids. All right. So we divide both sides by 4. We divide each term on the left by 4. 4x squared goes to x squared. 4y squared goes to y squared. Negative 16x goes to negative 4x. 4y goes to y. Negative 11 goes to negative 11/4. Sorry, there's a fraction there. And again, 0 divided by 4 is 0. But don't forget to put the equals 0. We have an equation here, okay? So that whole left side equals 0. Okay. Now, our leading terms on the left side are now x squared and y squared. At this point, we're going to group together the x stuff and group together the y stuff. We're going to group together the x squared and x terms over here. And we're going to group together the y squared and y terms over here. We'll indicate the groups with parentheses. And while we're at it, let's go ahead and add 11/4 to both sides so that we have our non-zero constant on the right. Notice I said add 11/4. Don't say move. If you say move, you might make the mistake of putting a negative sign there. We're adding 11/4 to both sides. To stress that, we're adding 11/4 to both sides. Don't say move. So we've grouped together the x stuff. We have the group x squared minus 4x, plus we group together the y stuff, y squared plus y, equals 11/4. Now, we're going to create PSTs for the x group and the y group so that the PSTs can be factored as squares of binomials. Well, how do we create PSTs? We CTS, all these acronyms. We CTS. We're going to complete the square in both the x group and the y group. So how do we do that? How do we complete the square? All right, well, let's take a look at this x group here. We have x squared minus 4x. We're going to add a number in here. We're going to add a constant in here in such a way that the result will be a PST. The goal is to get a PST for our x group here. Now, what is the trick to completing the square? It's an algorithm. You take the coefficient on x, which is -4. So take the coefficient of x, which is the -4. You take that and you cut it in half. You take half of that. Half of -4 is -2. And then what do we do with that result? We square it. The square, well, let's be careful. The square of -2 the square of -2 is what? The square of -2 is +4. The square of -2 is +4. Okay. So we add 4 to this first group. But wait a minute. I can't just add 4 to this left side of the equation just because I feel like it. I have to pay for it. I have to compensate for it. A quick way to do it, since we're adding 4 to the left side, let's add 4 to the right side. Now, similarly, how are we going to complete the square for the y group? Do this in green. What's the coefficient on y? The coefficient on y is 1. What's half of 1? It's 1/2. By the way, the sign doesn't matter because we're going to end up squaring anyway. We're going to be adding in both groups anyway. The square of 1/2, what's 1/2 times 1/2? That's 1/4. So we have to add 1/4 to this group over here. But if I add 1/4 to the left, what else do I have to do? I have to add 1/4 to the right. We're a real mess here. Here I've cleaned it up. Okay, so our first PST will be x squared minus 4x plus 4. And remember, when we add 4 to the left, we have to add 4 to the right. And then for the y group, y squared plus y, we add 1/4 to complete the square to make a PST. So that means that we have to add 1/4 to the right side to balance things out. Remember, we have to balance things out. Okay, don't forget to add the 4 and the 1/4 to the right-hand side as well. The goal is to balance. balance the equation. By the way, why is it that we do this? Why do we take these coefficients on x and y, take half, and then square the results? Why do we do that? So very quickly, here's why we do that.
Okay, by the way, my presentation here is correct, but I make this cleaner in the next video. So if this is a little creaky, I clean this up in the next video.
Okay, so consider a plus b all squared, right? The square of this binomial will be, careful, it's not a squared plus b squared, it's a squared plus what? Plus twice the product of the two terms, plus 2ab, plus now your b squared. And that thing there is going to be our perfect square trinomial. So if we're starting off with an a squared term, right, and an a term over here, really I should write this as plus 2ba. Okay, so we have the a squared here, right? 2b is the coefficient on a over here. What do we do to 2b to get the b squared over here? All right. To get from 2b to b squared, what do? You take half of 2b, and then you get b alone, and then you square the b to get b squared. Notice if I had a minus sign here, okay, I'd have a minus sign here, minus sign here. I'd have a negative 2b here, but then when we square, it wouldn't matter because when you square negative 1b, you still get b squared. So this works whether that's a plus or a minus. Okay. Instead of a, we had x, by the way. It might have been more helpful if I had put an x here. X squared over here 2bx. So a took the role of x, really. All right, so anyway, we take the coefficient on the a or x here, take half of that, and then square the result. That's why we, that's how we complete the square. That's how we CTS to get a PST, a perfect square trinomial. Lots of acronyms. All right. So let's get back to business now. Okay, well, these are PSTs. How do you factor them as squares of binomials? X squared minus 4x plus 4. That's the square of x. Then you grab the middle sign here. That's a minus sign. What's the square root of 4? 2. Okay. Another way to look at that, half of negative 4 is negative 2. That was that middle guy in the completing the square process, the b. Basically, you're going to end up putting b or basically plus or minus b in here, right? You're going to take half of this coefficient. So whatever this coefficient on x is here, you're going to put that half of that coefficient over here. Half of negative 4 is negative 2. Okay. You're basically taking the middle guy, whether it's a plus or a minus. You're going to take this middle guy. All right, x minus 2 all squared. Likewise over here, when you factor that, you're going to get y, the middle sign's a plus sign. Well, half of 1, that linear coefficient, half of 1 is 1/2. So we want y plus 1/2 all squared. Okay, observe that the square of 1/2 is 1/4. The square root of 1/4 is 1/2. So when we factor these two PSTs, we get the square of x minus 2 plus the square of y plus 1/2 equals 7. If you want to make this more closely match the standard form, okay, if you want to write this as the form y minus k, y plus 1/2 is y minus negative 1/2. But I would accept either as standard form for the equation of the circle. The situation is clearer either here or here than up here. Okay, this was a big old mess. I had no idea what the center or the radius were. But here, okay, so this is one form of an equation for the circle, but it's not very helpful. These are much better forms. These are standard forms for the equation of the circle. All right. From either one, what's the center of the circle? Remember, you're looking for values of x and y that will make the left-hand side equal to 0. That's the trick. We need x equals +2, and we need y equals -1/2. Basically, we need to do sign flips on these guys here, sign flips. So that's the center. I'll label that C. What's the radius? Is the radius 7? No, 7 is r squared. So what's r itself? R is the positive square root of 7. The center is at 2 -1/2. You need sign flips from the equation. The radius is the square root of 7, not just 7. It's 2 point blah, blah, blah. Irrational. That's okay. Meters, if you wish. Okay, we've done circles. Next, let's do lines. Next time.
All right. Any questions thus far? Any questions thus far? And actually, I have a couple of goodies to show you. Well, first of all, I want to clear up that CTS thing. Let me show you that. Let me show you that.
Hi, everyone. I wanted to clean up my explanation of completing the square. So when you square a binomial, x plus b, you get x squared plus 2bx plus b squared. So to complete the square, you take the coefficient on x, 2b, take half of that, you get b, square that, you get b squared. And that's what you add to complete the square, CTS. This is the completing the square process, CTS. And then to factor this back, you take the x. If b is positive, this is a plus sign. If b is negative, it's a minus sign. And then you take the principal square root of b, put it over here. Or a simpler way to do it, just grab the b, whatever this is, positive or negative, and it becomes this over here.
We take the square of the b square guy. I should have mentioned that. You take the square of the b square guy.
That's CTSing to obtain a PST. And I'm explaining how to factor back also.
Okay. So you want the square root of that to get, that. That's I got to make that correction there. Okay. And now I want to show you Desmos. This is going to be really cool. It's all cool, but let me.
Hey everyone, I want to show you a great free online tool, like a graphing calculator. It's at desmos.com, DESMOS.com. I'll click on graphing calculator. So let's say that we want to graph this black circle, x squared plus y squared equals 9. Remember that to get an exponent, you type in shift 6, which basically gives you the caret. All right, so x
not the one you eat
squared, I click the right arrow there, plus y exponent squared, right arrow, equals 9. And I can change that circle, its color. Oh, by the way, I can click on this disk here to make it appear and disappear, like a magic trick. If I right-click on this, or if I press on my MacBook, it's control. No wait, yes, it's control click. Control click, right? And then I can click on a color like black, for example, and change the color of the circle. By the way, if you want to change the window, you can go to the wrench over here in the upper right, graph settings. Projector mode makes it more suitable for projecting on like a video screen. The numbers are bigger, for example. And then you can also change the window. So you can choose different values of x coordinates you can see, different values of y coordinates you can see. All right, we can also graph this translated circle, x plus 2 all squared plus y minus 1 all squared equals 9. Parenthesis, x plus 2, end parenthesis, exponent, squared, right arrow, plus, parenthesis, y minus 1, parenthesis, exponent, squared, equals 9. That's in blue. I can control click, make it red, for example. Right? Okay. And I'm translating from the black circle to the red circle. And you can also plot points. For example, let's say I want to plot the point 3, 0, parenthesis, 3, 0, end parenthesis. So you see that's in green right now. And you see that green point there. I can change the color, control click. I can change it to orange, for example. Right? And I can label it. Labeled 3, 0. Okay. And the wrench can allow more options, like making it larger, for example. Okay. And changing where you put the label. You can make it vertical in orientation.
I just learned that.
Okay, Desmos. We're going to play with this free online graphing tool a lot. Go ahead and play with it.
In fact, while we're at it, I'll give you a few moments to check it out. Go to desmos.com, desmos.com. It's free, all right? Let you play with it for, about 20 seconds. Then we'll head off to lines. I have another fun video. Oh, and that keyboard thing, that's like that's like on your iPhone, right? You can type in stuff. You get lists of functions and square root, SQRT, right? Okay, so keep checking it out. All right, on the homework, check it out, see what you can do. All right, folks. So the next thing is 0.14 on lines. Well, let's start it this way. Review of lines. People need it.
Hi, everyone. Section 0.14 on lines. Let's start with some notation. Okay, so remember that two distinct points in the plane determine a line, this straight figure that connects the points. Let's assume that all these represent real numbers. So we have 2 points, x sub 1, y sub 1, the first point over here, and x sub 2, y sub 2, the second point over here. I might refer to them as p sub 1 and p sub 2. Of course, I can interchange the notations. Now, an important number, an important parameter for this line is the slope, denoted by m, if it is defined. Try to remember what kind of lines have undefined slopes. And remember, slope is what over what. We're going to talk about that next. Okay, so let's say we have a slanted or tilted line in the xy plane. What are arguably the 2 most important or interesting points on the line? Well, quite possibly the x-intercept and the y-intercept. Now, if you have a slanted line that goes to the origin, both the x-intercept and the y-intercept will be at the origin, 0, 0. But if the tilted line does not go to the origin, then the x-intercept and the y-intercept will be at distinct points.
I pointed them in the wrong order.
The x-intercept here is at A, or more precisely, the point A, 0, using ordered pair notation. Nowadays, when teachers ask you for an x-intercept, you're supposed to report an ordered pair. Here, A, 0, in parentheses. Likewise, when we talk about the y-intercept, it's tempting to talk about B, but technically it's the ordered pair 0, B, corresponding to this point here. As the name suggests, the x-intercept is the point where the line intersects with the x-axis. The y-intercept is the point where the line intersects with the y-axis. Okay, back to slope. What is the slope of a line? It is what over what? It is rise over run. M is the classic notation for slope. So we can think of the rise as delta y, the change in y. Here's delta y, the change in y. We can think of the run as delta x, the change in x. And actually, you can take either order as long as you're consistent. So here, it makes sense that for the rise, I take the y-coordinate on the right point and subtract off the y-coordinate on the left point. Okay, whether the right point is higher or lower in the xy plane. But if I say that y sub 2 is the y-coordinate of the right point over here, then x sub 2 better be the x-coordinate of that point. Likewise, x sub 1 better be the x-coordinate on the left point. So you can switch these ordered pairs. That's fine. But don't switch the x1 and the x2 without switching the y1 and the y2 also. They both come in packages. Okay, rise over run. That's a measure of steepness and direction. Rise over run. Change in y over change in x. Y sub 2 minus y sub 1, all over x sub 2 minus x sub 1. Or you could switch these and switch these. So you could write it as y sub 2 minus y sub 1 minus y sub 2, all over x sub 1 minus x sub 2. That's equivalent. Why is it equivalent? Because how is y sub 1 minus y sub 2 related to y sub 2 minus y sub 1? They are opposites, meaning that they differ by a factor of -1. Likewise, x sub 1 minus x sub 2 is the opposite of x sub 2 minus x sub 1. It's like we're multiplying by -1. So basically, if you go from this fraction to this fraction, you're just multiplying the top and the bottom by -1, basically, and that's legal. You're multiplying by 1. Okay, so in this example here, the rise is positive. If the point up here were down here, then actually the rise would be negative. We really have a drop, and the slope would be negative. Okay, usually we take the run to be positive, and then the sign of the rise would be the sign of the slope. That's the basic idea. We usually take the run to be positive. The larger x-coordinate minus the smaller x-coordinate. Right. Again, delta means change in. Delta y over delta x. Not y over x. It's change in y over change in x. There's a physics teacher in North Carolina who got on physics textbook authors to change that. It's not y over x. It's change in y over change in x. We're relating changes. Basically, a slope indicates a rate of change. It's change in y with respect to x. All right. Here's a related idea. This may be the most important thing about slope that you don't know yet. The interpretation of slope m as marginal change. So, for every unit increase in x along the line, y will change by the slope, m. So for example, let's say that I take any point on the line. Let's say this point here, x sub 1 comma y sub 1. Let's say that I run 1 unit to the right, to the east. Well, how do I have to change my y-coordinate to get back onto the line, to get back onto the path? I have to change my y-coordinate by m, the slope. If m is positive, I go up. If m is 0, I stay horizontal on this line. If m is negative, I go down. So for example, and this is an application in economics, here's a linear function that expresses the house value in dollars with respect to time in years. I should put units, maybe the year 2000. corresponds to the x-axis here. Whoops. Maybe the year 2000 corresponds to the x-axis here.
Because I should say y-axis.
And maybe the y-intercept here is at, I don't know, $200,000. So in the year 2000, on January 1st, 2000, the value of the house was $200,000. And let's say that the value of the house has increased linearly by this rate of change, $10,000 per year, linearly. Which means that every time the time increases by 1 year, like so, the value of the house increases by $10,000. Like so. All right. 1 year, $10,000. 1 year, $10,000, and so forth. So we can interpret slope as a marginal change. If the x-coordinate, or t-coordinate maybe, increases by 1 unit, how much does the y-coordinate, change by? And that's indicated by the slope. All right. Interpreting slope as marginal change. That's very useful. That's related to the idea of differentials in calculus. Where you use tangent lines to model behaviors of curves. All right, so how can we interpret slope? Well, first of all, you have a positive slope when the line is going up, if the function is increasing. The slope is 0 if we have a flat line, a horizontal line. And the slope is negative if the y-coordinates are dropping with respect to x. The absolute value of m, the absolute value of the slope, measures the steepness of the line. So one way I look at it, you can think of the slope as the difficulty with which you can move a car from left to right. So for example, on this horizontal line, the slope is 0, okay? Let's say the car is in neutral, you're pushing the car. Difficulty level 0. Well, if you have a hill where the slope is 1, it's going to be harder to get the car from left to right. If the slope is 2, that's even steeper. It's even harder to move that car. Slope equals 3 pi. Slopes don't have to be integers. Slopes could be irrational as well. 4, 5, approaching infinity. All right. Actually, we say that the slope of a vertical line, like the y-axis, is undefined. But in a way, the slopes are approaching positive infinity. Let's play with Desmos. We can do that. Let's go into Desmos. All right. Y equals mx. I'll add a slider. Whenever you put in a parameter like m, you can add in a slider, right? So here's y equals 1x. Here's y equals 2x. Y equals 3x. It's getting steeper, right? Here's y equals 3.2x. Y equals 3.5x. Getting steeper, 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 all right? Y equals 10x is very steep. All right. How about y equals, oh, and of course you could just type it directly, right? Like y equals 10x. In green, that's superimposed over the red line. I'll flash red, green like that. Okay, same line. If m is set to 10. Let's move the slider back. What's y equals 0? Y equals 0x or y equals 0? We're down to a flat horizontal line, the x-axis. Right. So y equals 0, that's the x-axis. Basic principle of graphing. The graph of an equation consists of all points whose coordinates satisfy the equation. The x-axis consists of all points with y-coordinate 0. 0, 1, 0, 2, 0, 3, 0, pi, and so forth. All right. Now, what about negative slopes? Well, here m equals -1. So it's fairly easy to drop the car. If the car is in neutral, you can just let go. If m equals -2, if that's a steeper negative slope, okay, so the car drops down pretty quickly. So let's go backwards. M equals -1x. M equals -1. M equals -1x. M equals -2x. That's steeper. Line's going down. Okay, the slope gets more and more negative. The slope's approaching negative infinity, approaching a vertical line. Here's y equals negative 10x. Put a negative sign there. The green line, y equals negative 10x. All right. And again, the vertical line here, like the y-axis, undefined slope. What's the equation of the y-axis, by the way? It's going to be x equals 0. Because the y-axis consists of all points whose x-coordinate is 0. The origin, 0, 0, 0, 1, 0, 2, 0, 3, 0, pi, 0, negative pi, and so forth. All right, again, the slope is undefined for this guy. For vertical line. Because there's no run. The run is 0, rise over run, you're dividing by 0. So slope is undefined. I don't care what the rise is. This is garbage. Slope is undefined. All right. Hi, everyone. This isn't mine, but look at Mr. Slope Guy. Why is this Mr. Slope Guy? Now, these are line segments, not full lines, but take a look here. We have a rising line segment. The slope is positive. The slope is positive. We have a falling line segment. The slope is negative. A vertical line has what kind of slope? Undefined. We're going to give this guy a red nose. Undefined slope. Undefined slope. Okay. Horizontal, 0 slope. So positive slope, negative slope, undefined slope, 0 slope. Okay, well, I'm really beating this guy up, but this is Mr. Slope Guy. Hi, everyone. Question. How do you graph x equals 2, and how do you graph y equals 2? Use the basic principle of graphing. I'll give you a hint. The graph of x equals 0 is the y-axis because the x-coordinates are all 0 here. The equation of the x-axis is y equals 0 because these are all the points where the y-coordinate is 0. So the graph of x equals 2 will be parallel. The graph of x equals 2 will be parallel to the graph of x equals 0. They're both going to be vertical lines. Likewise, the graph of y equals 0, the x-axis, is going to be parallel to the graph of y equals 2, which will be a horizontal line as well. The basic principle of graphing. The graph of x equals 2 will be a vertical line because points include 2, 0, 2, 1, 2, 2, that intersection point, 2, 3, 2, pi, 2, negative pi, and so forth. All the points with x-coordinate 2 form this vertical line. Likewise, all the points with y-coordinate 2, think function, all the points with y-coordinate 2 will lie on this horizontal line. 0, 2, oops. 0, 2, 1, 2, again 2, 2, which lies on both. 3, 2, negative 3, 2, and so forth. So remember the basic principle of graphing. It helps here because a lot of students mess these things up. In calculus, you're going to be asked to take plane regions and revolve them around axes. You better know which is which. All right, let's go to Desmos. Of course, Desmos knows. All right, So here we have x equals 2. Let's do that in blue. We have y equals 2 in red. Okay. And they intersect in the point 2, 2. And I'll label it. By the way, you can zoom in or zoom out. Okay? Or it might help also to go to projector mode over here. That makes things a bit clearer. All right. Horizontal and vertical lines. Be careful what their equations are. And remember, the slope of a horizontal line is 0. Rise over run. Remember, slope is rise over run. Slope is rise over run. On a horizontal line, the rise is always 0. So the slope is 0. Okay. But the run can always be taken to be positive. However, for a vertical line, remember Mr. Slope Guy? The slope is undefined. The slope is undefined because the run is always 0 on a vertical line. The slope is 0 for a horizontal line. The slope is undefined for a vertical line. Next up, what do we do about slanted or tilted lines? Next time.
All right, let's go ahead and take a break. I'll see you at 8:30. Just do this. And mute. Mute if you have to use the restroom. All right. And while we're at it, and before you go, there's something else I wanted to show you actually. On this. I'm just moving these triangles around. How come I'm getting one more square unit of area? Think about that. Okay, hold on. Let me, okay. Well, let me, where did I put that? There we go. Take this. All right. All right. We'll start soon. Take a look here. Do you see the trick? I'll give you a hint. These aren't really triangles, and they're not really congruent. And I'll give you a key word here. The word is slope. Do you see the trick? All right. Do you see the problem? See, we have different slopes here. So here's the thing. Look at the blue triangle, right? The slope of the hypotenuse, rise over run, 2/5. The slope of the hypotenuse for the blue triangle is 2/5. The slope on the red triangle, on the hypotenuse for the red triangle, is 3/8. 2/5 and 3/8 are different slopes. They're different slopes, which means that the big figure here and the big figure here, they're not really triangles. They're not really triangles. So you can't really compare area directly like that. Okay, sneaky. We're being sneaky here. All right. So let's go on. More with lines.
Hi, everyone. How can you write an equation for a line? There are many different ways. For example, here's general form. For example, 2x plus 3y equals 4. Here's the graph of 2x plus 3y equals 4. It's a tilted line. If just one of these coefficients is 0, you get a horizontal or a vertical line. If both of these are 0, you don't have a line. Now, I have a question for you. If I have a line and you care, what are a couple of hints I could give you so that you can figure out the equation of the line in the xy plane? If I give you a what on the line, and if I give you the what of the line, what pair of bits of information? Well, maybe if I give you a point on the line, any point on the line, and if I give you the slope, I'm assuming the slope is undefined. I'm assuming that the slope is defined. If the slope is undefined, you know that you have a vertical line, in which case you can figure out the equation anyway. It's the equation of a vertical line. Let's assume that we have a tilted line and the slope is defined and not 0. Point slope form. What is the point slope form for the equation of a line? Let's say that x sub 1 comma y sub 1 is a point on the line and m is the slope. In fact, m could even be 0, but let's assume for now that m is not 0. M is defined. Now notice that if you were to divide both sides of this by x minus x sub 1, then you would get that the slope looks like this kind of difference quotient here, change in y over change in x. So basically, we want all points x comma y that will force this constant ratio as a slope. So you have a point, you connect it with the key point x sub 1 comma y sub 1. You want all points x comma y that will force a slope m with this given point, x1, y1. So that is point slope form. Y minus y sub 1 equals m times the quantity x minus x sub 1. Point slope form for a line, where m is defined. Now, if we have a slanted line that does not go through the origin, what are the two most important points on that line? Many people would say. Well, quite possibly the x-intercept and the y-intercept. If I give you the y-intercept and the slope, then you're in business. You can find the equation of the line. All right, slope-intercept form, where we use the y-intercept. Slope-intercept form, y equals mx plus b, where the ordered pair, 0 comma b, technically, is the y-intercept. Y equals mx plus b. So for example, let's consider y equals 2x plus 3. Okay? Y equals 2x, that has slope 2, but it goes to the origin, 0 comma 0. Y equals 2x plus 3, that goes to the point 0 comma 3 as the y-intercept. If I have y equals 2x plus 4, then it goes through 0 comma 4 as the y-intercept, and so forth. I could put a slider here, 0 comma b. Put a slider here. If I slide b, then I change the y-intercept. I can put in an m slider over here. Y equals mx plus b. I have two sliders. One slider for slope, one slider that affects the y-intercept. Together, I can get all possible non-vertical lines. Y equals mx plus b. If you have a big old slider for m, big old slider for b, you can get all possible non-vertical lines in the xy plane. We have two parameters for this slope-intercept form for the equation of a line. The slope m and the y-intercept given by b, or 0 comma b. Here's a more exotic form, 2-intercept form. Again, if you take a line like 2x plus 3y equals 4, a slanted or tilted line that does not go through the origin will have an x-intercept and a y-intercept that are distinct and not at the origin. Okay. Well, if a comma 0 is the x-intercept, and if 0 comma b is the y-intercept, here's another form. Observe that a comma 0, the x-intercept, satisfies this equation. 0, comma b would also satisfy this equation if b is not 0. It's a bit exotic, but it's there. Two-intercept form for a tilted line that does not go through the origin.
To state it, it's x over a plus y over b equals 1.
Next up, the classic problem. Given two distinct points, and they're going to determine a line in the xy plane, find an equation for such a line. There's only one line that can do it, but they're different forms. Let's find different forms for the equation of the line, or an equation of the line that goes through these two distinct points in the xy plane. Next time.
Any questions before we go on to this key problem here? Any questions? Okay, let's go on.
Hi, everyone. Let's do the classic problem. Given two distinct points in the xy plane, find the slope-intercept form of the equation of the line that passes through the 2 points. -4, 5, and 2, -6. Let's plot them here. -4, 5, and 2, -6. All right. Okay. So I want to find the equation of the line that connects these 2 points. Imagine I'm playing a video game. How did I get this guy to shoot at this guy? I'm playing a video game. Okay. Let's find the slope-intercept form for the equation of that line. This line has many equations we can attach to it. I want this form. Well, it would help if I found the slope, right? Slope is rise over run. So it's change in what over change in what? It's change in y over change in x. It's rise over run. Okay, the slope is delta y over delta x. Please remember not to flip these. That's a very, very common error. I'll put this in red. Do not switch these, capital. Do not switch these, because it's an extremely common error in exams that people put the delta x on top just because they're thinking alphabetically. Remember, slope is rise over run. It's change in y over change in x. Now, you can take the difference in either order. You can either go -6 minus 5 or vice versa, but be consistent. Whatever order you go in on the top, you better match that order in the bottom. If you go -6 minus 5 on the top, that's fine, but that means that you have to go 2 minus -4 on the bottom. If you do it in reverse, you're going to mess up your sign. All right, so in the end, we have, well, the rise, -6 minus 5 is -11, over the run is going to be 2 minus -4. 2 plus 4 is 6. So you could say that if the run is 6, then the rise is -11. Really, it's a drop of 11. The slope is -11.6. By convention, we normally pop out that -1 factor out here. The slope is -11.6. So on Desmos, I could say I know y equals, I know y equals -11/6 times x plus something. All right, and then maybe with a slider, I can kind of figure it out. And there you go, that's an approximation. Okay, b is about -2.3, but let's get it exactly, all right? Let's play the video game exactly. But we think b is going to be about -2.3. Desmos is no fair. Don't just appeal to Desmos on your homework. Okay, you can play with Desmos, but don't say in your homework, oh, I use Desmos. Okay. All right, anyway, the slope is -11.6. Now, I want slope-intercept form, but in the meantime, I have the slope and I have 2 points. I have an abundance of riches. I can pick either of these 2 points and write out a point-slope form for the equation of the line. Again, I could use either of these 2 points or whatever else, whatever other point I happen to find on the line, and I can use this slope. All right. What is the point-slope form? It goes right, y minus y sub 1 equals m, the slope, times the quantity x minus x sub 1. And I'm choosing to use the first point, -4, 5. Now again, be careful. The -4 goes in here. It's the x-coordinate x sub 1. The 5 goes over here on the left in the y sub 1. Again, a lot of people switch these up. The slope, we already found that. The slope was -11.6. All right, so then we get y minus 5 equals -11.6 times the quantity x minus -4. And that would count as point slope form. Now, for some homework problems, that might be enough if I just wanted an equation for the line. Well, I can go into Desmos, for example. Y minus 5 equals -11.6 times the quantity x plus 4, or x minus -4, or x plus 4. Okay, and that's going to be the line exactly. But that's in point slope form. In the homework or in the problem here, I'm asking for slope-intercept form. So now it's a matter of mechanical algebra. How do I get from here to slope-intercept form? Which is y equals mx plus b. Okay, let's do some cranking here. First of all, x minus -4, that's x plus 4. Cleaning up the signs there. Okay, and while we're at it, I have y minus 5 on the left. In the end, I want y all alone. So why don't we go ahead and add 5 to both sides? Don't say move, say add. We're going to add 5 to both sides. So then we get y all alone, -11.6 times the quantity x plus 4, all plus 5. And now we can distribute. Again, our goal is to find something of the form y equals mx plus b. All right, let's take the -11.6 and use what D word? Let's distribute that over the sum. -11.6 times x is -11.6. That's easy. The hard part is,
X.
what's -11.6 times 4? Or more simply, 4 over 1. That might be easier. 4 over 1. In fact, we can do some cross-canceling. 4 divided by 2 is 2. 6 divided by 2 is 3. We're allowed to do this kind of cross-canceling. So in the end, we get -11 times 2 is 22. 3 times 1 is 3. In the end, we can reduce by dividing the top and the bottom by 2 anyway. We may as well do it while these factors are separated like that. We may as well divide the 4 here by 2. We may as well divide the 6 down here by 2. In any case, -11.6 times 4 will be -22/3. All right, this is -22/3. Now, in order to add the 5, I like to get this in terms of thirds. 5 over 1 is what over 3? Well, 1 times 3 is 3, and 5 times 3 is 15. I'm basically taking 5 as 5 over 1. I'm multiplying by 3 over 3, or 1, and I'm getting 15/3. That's this over here. All right. Now, what is -22/3 plus 15/3? It's like a weird Vegas game. You lose 22/3, you win 15/3, you still lose 7/3. But look at this. Y equals -11.6 minus 7/3.
-11.6x.
Slope-intercept form.
I don't know why I keep missing the
I mean,
x.
yeah, you could write this as plus -7/3, but minus 7/3, I'm happy with that. Y equals -11.6x minus 7/3. That's slope-intercept form. We knew the slope was -11.6. What do we know now? The y-intercept is at 0, -7/3. All right, so I want the line y equals -11.6 with the right arrow, right? Parenthesis x, b equals negative 7/3. There you go. That blue line does a perfect job. And here's the y-intercept, 0, comma, and there's the decimal approximation of negative 7/3. Perfect. This blue line is perfect. Slope-intercept form is unique. So if you write down the slope-intercept form, your friend writes down the slope-intercept form, you better get the exact same thing. Well, your friend, if your friend's a stickler, instead of negative 7/3, you could do this, but I think this is overkill. But aside from that, your friend better get what you get over here. Slope-intercept form is unique for a given line, a given slanted line. But what about point slope form? Was that unique? The answer is no. For one thing, instead of negative 4, comma 5, I could have used this other point, 2, comma negative 6, which, by the way, would have led me to the same slope-intercept form as well. Or for that matter, you could use any other point, any of the infinitely many other points that happen to be on the line. Okay. I call that method 1. We're going to go to method 2 and show you a faster way of doing this next time.
All right, any questions about this, though? Any questions about this? All right, I'll try to remember to say X from now on. Faster method next.
Hi, everyone. Here's a faster way of doing the problem that we just did. Again, we want to find the slope-intercept form for the line that goes through the two given points, negative 4, comma 5, and 2, comma negative 6 over here. Now, we have to find the slope. With either method, you have to find the slope. So if you haven't found it yet, find it. Slope is rise over run, negative 11/6. We still need that. But now, since we want something of the form y equals mx plus b, we have the value for m. Well, shouldn't we be able to find b fairly quickly? And it turns out we can. The basic principle of graphing. The graph of an equation consists of all points whose coordinates satisfy the equation. That includes negative 4, comma 5. Or maybe this other one here, 2, comma negative 6. Again, you have your choice as to which one to pick. So let's plug in. I know the slope is negative 11/6. That's a direct substitution. And I know that b has to have the property that it has to make this equation true. So that when y equals 5, I'll put this in green, so that when y equals 5 and x equals negative 4, in parentheses, these two numbers are multiplied together, put parentheses, then I know that b has to satisfy this equation. Solve for b. Solve for b. Again, we have to mess with fractions a bit. Negative 4, you can think of as negative 4 over 1. You could do some cross-canceling. Or recognize that we're going to get 22/3, right? Like before. We're going to get 22/3. So we have 5 equals positive 22/3 plus b. How do we solve for b? Don't say move, say subtract the negative, say subtract the 22/3. Anyway, we're going to zap this stuff over here. We're going to subtract the 22/3, whatever that mutated thing was. Okay, b is going to be 5 minus 22/3. Okay, 5 minus 22/3. 5 again was 15/3. I mean, I'm doing some of the arithmetic I did before, so this might be a slight exaggeration of how much faster this is, but I do claim it's more efficient. Even if I hadn't been repeating the arithmetic here. 15/3 minus 22/3 is negative 7/3. B is negative 7/3. So I know that if I play this Desmos game, I love these Desmos games, y equals negative 11/6, right arrow, parenthesis, x plus b. What should b be? What should b be? It's like the Price is Right. Something like that, right? Something like about negative 2.3. Well, we found out that it's exactly negative 7/3. All right. So straight up, minus 7/3. And that does a better job, that green line. All right. Now, we're not done yet. You have to take this value for b and plug it in. And also the value for m. Y equals mx plus b. The x and the y stay in there. They're variables. But we need to find the particular values, the constant values for m and b. M and b are constants here, but they're unknown. They're fixed but unknown constants. And we want to find out what they are. We found out early on that m was negative 11/6 from our early work. Okay, we now find b is negative 7/3. Plug those values in. M is negative 11/6. B is negative 7/3. Don't forget to plug them in. Plug in. A lot of students get lazy and they forget that. Plug in the values for m and b, and this is your final answer. Y equals negative 11/6x minus 7/3. The same answer that we got before. Remember, slope-intercept form for the equation of a line will be unique. A non-vertical line.
Great. Any questions before we go on?
That's faster.
Yeah. Any questions before we go on? Any questions? We'll finish up lines in a moment. All right. All right.
Hi, everyone. Try to remember parallel and perpendicular lines. If I have a line of slope 3, this guy's kind of steep, what will be the slope of any parallel line, and what will be the slope of any perpendicular line to this line? I'm assuming that we're in the xy plane. Well, a parallel line will have the same slope. All parallel lines will also have slope 3. And all vertical lines are parallel. Yes, vertical lines have undefined slope, but they're still parallel. So otherwise, if they're not vertical, two lines are parallel in the plane if and only if their slopes are equal. But what will be the slope of any perpendicular line in the plane? It's going to be negative, slightly negative, kind of flat actually. Perpendicular, by the way, means that it makes a right angle with a given line, indicated by this box. The slope of any perpendicular line will be the opposite reciprocal. The opposite reciprocal of 3 is negative 1/3. Opposite reciprocal. You take the reciprocal and take the opposite sign. All right. Bear in mind, a horizontal and a vertical line are perpendicular. But again, the vertical line has undefined slope. Otherwise, two lines are perpendicular, and that's often denoted by this upside down T here, if and only if their slopes are opposite reciprocals of each other. So parallel lines, denoted by this, parallel lines have equal slopes, or they're both vertical. Perpendicular lines have slopes that are opposite reciprocals, or you have this kind of deal. Right. So again, this blue line has slope m equals 3. The purple line is parallel. It also has slope m equals 3. The red line here is perpendicular. It has slope negative 1/3. So for the blue and the purple line, if you run 1, you have to rise 3 to get back on the line. For the red line, if you run 3, you have to drop 1 to get back on the line. Perpendicular lines. All right, well, negative 4/7. A line of slope negative 4/7 is perpendicular to any line of slope positive 7/4. How about negative 13/17? If I have a line of slope negative 13/17, what would be the slope of any line perpendicular to it? The answer is positive 17/13. Opposite reciprocals. Oh, by the way, this is a square, and the diagonals are perpendicular. Huh? How's that possible? That's a square, and the diagonals are perpendicular. It's true that the diagonals of a perpendicular are square. These are perpendicular. How's that possible? 0, 1, 2, 0, 1, 2. This is a square. You can't argue with me, right? 1 meter, 1 meter, 1 meter, 1 meter. That's a square. And the diagonals are perpendicular. The thing is, if you have unequal scales on the axes, then notions of congruence and perpendicularity may be lost. Your eyes won't be able to see them. All right. Hi, everyone. Okay, you have a slanted or tilted line that does not go through the origin. A lot of people would say that what 2 points are the most important points on the line? A lot of people would say the x-intercept and the y-intercept. Well, how do you find them? Finding intercepts. Well, if you want to find the x-intercept, you want to know where the line intersects the x-axis.
Uh-oh, what happened here? Buffering, really?
What's the equation of the x-axis? I put this on exams. What's true of every point on the x-axis? The y-coordinate is 0. The equation of the x-axis is y equals 0. And the equation of the y-axis is x equals 0. The y-axis consists of all points whose x-coordinate is 0. The basic principle of graphing. Hence, to find x-intercepts on a graph, whether it's a line or something else, to find x-intercepts, you set y equal to 0. You set the other letter equal to 0. To find y-intercepts, you set x equal to 0. Again, you set the other letter equal to 0. And you solve for y. All right. Because the x-axis has equation y equals 0, the y-axis has equation x equals 0. So for example, the line 2x minus y equals -4, right? How do we find the x-intercept? Set y equal to 0. Quick, what's x? X equals -2. We divide by 2. So to find the x-intercept, you plug in y equals 0 and solve for x. Plug in 0 for y, substitute in, x equals -2, which means that the x-intercept is denoted by the ordered pair -2, 0. Technically, we write it as an ordered pair. How about the y-intercept? We plug in or substitute x equals 0 and solve for y. So we put in 0 for x, solve for y, y equals +4. So the y-intercept is given by the ordered pair 0, +4. And since we have these two distinct points, we can then draw the line. Here's -2, 0. Here's 0, 4. Well, what's the line? The line is 2x minus y equals -4. Yep.
All right, I'm going to go to geometry now. First, I got to show you a clip from one of the funniest films from the 80s. It starred John Cusack.
Hi, everyone. I expect you to remember all of your formulas from plane and solid geometry. So that would include, in plane geometry, things like area and perimeter for things like squares, rectangles, parallelograms in general, triangles, trapezoids. The area of a trapezoid is the average of the bases times the height. Did you remember that? Circles. The area of a circle is pi r squared. The circumference of the circle, the distance around, is 2 pi r. Three-dimensional solid geometry. Know the formulas for the volume and surface area of a rectangular box. Right circular cylinders. Right means that it's not tilted. Circular means you have circular cross sections, right? With base radius r and height h. Know the volume, which is like capacity. Lateral surface area. Imagine a soup can. The lateral surface area is like the area of the soup label on the soup can. The total surface area consists of the lateral surface area plus the area of the top lid and the bottom lid, the circles there. That's why I have the plus 2 pi r squared. For a right circular cone, know that the volume of this cone is 1/3 of the cylinder that it fits snugly in, the circumscribing cylinder, and you can prove that using calculus. However, I will not expect you to know the surface area formulas for this kind of cone. Spheres, you gotta memorize these. The volume of a sphere, capacity, 4/3 pi r cubed. Surface area, imagine that you're wrapping up the bowling ball, all right? 4 pi r squared. Now, one way to not confuse these formulas, think in terms of meters. Like, for example, let's say the radius is measured in meters, right? Then r squared would be measured in square meters, which is a natural measure for surface area. The 4 pi is just a constant. R cubed would be in cubic meters. Again, the 4/3 pi is just a constant multiplier. So these exponents here, as a check, you can check your exponents to see if your formula makes sense for surface area or volume. Take a look at the volume of the cylinder here. Pi is a constant, r squared is in square meters, h is in meters. Together you have cubic meters, and that would be reasonable for the volume of the cylinder. Some people call that dimensional analysis, to make sure you have the right exponents. On exams, people would often mess up their exponents. Or they would put down something that would end up being 4-dimensional. That would make no sense. For the surface area of a box, okay, imagine a room, a pretty boring cubicle, right? It's the total area of the walls, the ceiling, and the floor. 6 sides, 6 areas, add them up for the total surface area for the rectangular box. For a cylinder, like the lateral surface area for a cylinder, imagine this. Imagine a soup can with a label around it. Imagine slitting the label perpendicularly to the base. Spread out the label and you get a rectangle. The distance around that circle, that circumference, becomes the base of the rectangle, 2 pi r. The height is still h. The area of the rectangle is 2 pi r h, and that is the lateral surface area for the cylinder. To get the total surface area, add 2 pi r squared for the 2 circular discs. The volume of the cone is 1/3 of this guy, the circumscribing cylinder. Know these formulas, except for these surface area ones for cone. Don't worry about those, but know all the others. They're totally fair in pre-calc and calculus. Hi everyone. Section 0.16 is on variation, which uses a lot of terminology from physics. So, this model, y equals k.
Well, first of all, I would like to ask if there are any questions. Lines, geometry, know the formulas. Of course, we don't have exams, that helps, but any questions? Variation in physics.
Times x. This indicates that y is directly proportional to x, or y varies directly as x. Y equals k times x, where k is some non-zero constant of proportionality, or variation. That's a lot of words. Here's a basic example. Tipping. Now, if you're Steve Buscemi in Reservoir Dogs, you don't tip, but K equals 0. But let's say that you tip 15%. I've had servers who said 20%, 25%, 30%. But let's say you tip 15%, okay? Then K equals 0.15, where X is the value of your meal and Y is the actual tip that you give the server. So your tip as a dollar amount is directly proportional to the value of your meal. Y is inversely proportional to X, or Y varies inversely as X, if and only if Y equals K divided by X for some non-zero constant K. Z is jointly proportional to X and Y, or Z varies jointly as X and Y, if and only if Z equals KXY for some non-zero constant K. It's like a double multiplication. Okay, example. H is directly proportional to V and is inversely proportional to the square of R. And first of all, we can find a general model where we write this as a single equation. In fact, let's do that right now. Let's write down the general model. H is directly proportional to V. That means H can be described as K times V and is inversely proportional to the square of R. It's assumed that we write this all in a single formula, a single equation, and is inversely proportional to the square of R squared. By the way, this notion of inverse square laws, you see a lot in physics in the context of gravitation, electromagnetism. For example, let's say that you have a light source here. Here's a light source. It's a beaming light source. Hopefully not the sun. You're not supposed to stand too close to the sun. But let's say that you are here. You're standing pretty close to this light source, this lamp or whatever. Right? And let's say that your friend over here, is standing 3 times as far as you are from the light source. Now, is your friend getting 1/3 of the light intensity? No, it's an inverse square law. Your friend is getting 1/3 squared, or 1/9 of the light intensity. So inverse square laws are things that you see a lot of in physics. Anyway, now that's a general model, but we can find the value for K, which we often have to do. We have to find the actual value of this constant of proportionality if we're given particular data. Find the particular mathematical model related to this statement, that is, find K, if H is 2, when V is 18 pi and R is 3. So what do? We take the general model, plug in these values, and solve for K. Let's do that. We plug in H equals 2, V equals 18 pi, H equals 2, V equals 18 pi, and R equals 3. Don't forget to square the 3. We have R squared down there. And then you solve for K. You can do it in different ways. For example, you might note that 3 squared is 9, right? 18 divided by 9 is 2. So we have 2 equals 2 pi K. We want to solve for K. So what do? Don't say move. Say divide by 2 pi. Divide by 2 pi on both sides. K alone is on the right side. We have 2 over 2 pi here. How can we reduce this? Boom, boom. So do we get pi over there? No, it's 1 over pi. That's why I like to put 1s. The parentheses might be overkill, but at least put a 1 up there. K is 1 over pi. So we have our constant of proportionality. We're not done yet. It's like finding b in that line problem. We have to plug this into the general model that we got way up here. K is 1 over pi. Plug that in and simplify if necessary. So we take this general model, plug in 1 over pi for k. But we don't like this because it's a compound or complex fraction. Let's multiply by pi over pi. We're multiplying by 1 creatively in such a way that we're going to get rid of that little denominator there. 1 over pi times pi is 1. We still have the v up there. And then the pi down here moves over with the r squared. So we get h equals v over pi r squared. If you want to be cute, you can multiply both sides by pi r squared. Turn it around. What formula is this? I hope you remember. V equals pi r squared h. Pi r squared, that's the area of a circle times a height, volume of a right circular cylinder with base radius r for that circle down there and height h. I was being cute. Not all of my formulas or equations will be that significant.
All right, so here's the deal. So the intent is that you would review 0.11 and 0.12 on your own because it would take like weeks to review all of it comprehensively. But folks, I did make short videos here that skim over these things like in 16 minutes. So if it's worthwhile, you can stick around or watch these on YouTube. But I will skim over these in these videos. But the intent was for you to look over these on your own on my website. But here are 0.11 and 0.12 on equations and inequalities. After this, I will take questions, but we're going to go past 9:30. Feel free to chat at me because some of you may have questions. I'm going fast.
Hi, everyone. I'm expecting you to review 0.11 and 0.12 on my website, but let's do a quick overview. 0.11 is on solving equations. Now, when we talk about solving an equation in X, say, we were looking for all real solutions that will make the equation true. And when we solve an equation, the answer to solve an equation problem is given by a solution set, the set of all solutions. So for example, if you're asked to solve the equation 2x equals 6, there's only one real solution to that, x equals 3. Well, 3 is the sole solution. Our solution set consists of the sole number 3. We can check it out if we want. Plug in 3 for x, and it checks out. 6 equals 6. Now, if you have an equation like x equals x plus 1, well, there are no real numbers that equal themselves plus 1, so the solution set is the empty or null set. That happens sometimes. On the other hand, if you have something like x plus 1 equals x plus 1, all real numbers work out for x, so the solution set is R, the set of all real numbers, which you can also write in interval form like this, the set of all real numbers. This is called an identity, by the way. Now, before, in the earlier parts of chapter 0, we talked about simplifying an expression. For example, if I told you to simplify the expression 2x plus x, your answer might be 3x. On the other hand, if I tell you to solve the equation 2x plus x equals 3x, I'm asking you, what are all the real values for x for which the left side will equal the right side? Well, all real numbers. Our answer to a solve an equation problem is a solution set, which here is R. So remember, there's a difference between simplifying an expression, in which case we'd say 2x plus x is 3x, and solving an equation, in which case we'd say the solution set to this equation is R. So far we've been looking at linear equations, where we didn't have x squared or x cubed or anything like that. Well, how do we solve quadratic equations? Equations that can be written in the form ax squared plus bx plus c equals 0, where a is non-zero and a, b, and c are real coefficients. Well, we can use the quadratic formula, given famously by this. X equals the opposite of b, plus or minus the square root of this thing, the discriminant, b squared minus 4ac, and that's all over 2a, all over 2a. Please don't do this. Make your fraction nice and long there. So for example, we could use the quadratic formula to solve this quadratic equation. But in order to prep this equation, we need what on the right-hand side? We need a 0 there. So we have to subtract 15 from both sides. When you subtract 15 from both sides, then you get this equation where we have 0 on either the left or the right side. And then we can apply the quadratic formula. All right. We should identify the coefficients. A equals 2. B equals 7. Sorry, B equals negative 7. It's easy to mistake signs. That's why it's good to write these out. And C equals negative 15. Not positive 15, which might have confused people up here. C is negative 15 because you have to look at the form where 0 is isolated on one side. And then when you plug in, notice that the discriminant, 169, is a nice perfect square. We end up with rational solutions, negative 3/2 and 5. The solution set consists of those numbers, separate by commas, put braces. We take both the plus case and the minus case. Now, because the discriminant was a nice perfect square, we could have used the factoring method. The zero factor property helps a lot. If I have two quantities that multiply to 0, then that means at least one of them has to be 0. That's the zero factor property. Again, we need to isolate 0 on the right side, or one of the sides, because we have a zero factor property, not a 15 factor property. For example, 3 times 5 could be 15. Over here, we can factor this cutie, like so. Set each factor equal to 0, solve, and we get the same two solutions. By the way, it doesn't matter what order you put these solutions in. All right. So because the discriminant was a nice perfect square, 169, we got rational numbers as our solutions. If the discriminant is 0, meaning we have a PST here, we just have one double root. If the discriminant is negative, we have two imaginary solutions. That's for later. The square root method. If you're solving something like x squared equals 3, then the solutions will be given by plus or minus the square root of 3. Don't forget the plus or minus. Now, if you have something like x squared equals negative 3, well, remember, squares of real numbers are never negative. This cannot happen. Solution set is the empty set. So using the square root method, if there's no x term, solve for x squared. You get x squared equals 4/3. Use the square root method. Plus or minus the square root of 4/3. Simplify that radical. Rationalize the denominator. Here we multiply by root 3 over root 3. And we get our solution set. Although quite frankly, if you end up with this here, that might be more convenient, but technically our solution set should be written like this. The complete the square method can also work, especially if A is 1 and B is even. It can work pretty nicely, so you can look that over. When solving rational equations, for example, 9 over x cubed equals 1 over 4x, you might want to look for the LCD, the least common denominator. X cubed and 4x, in a way the smallest thing they both divide into nicely is 4x cubed, the LCD. Both x cubed and x go nicely into x cubed. We can multiply both sides by 4x cubed with the understanding that we can do that as long as x is not 0. we end up with x equals plus or minus 6. Neither one of these is 0, so these are both legal. These tentative solutions are in fact true solutions. This is our solution set. If we had gotten x equals 0, we'd have to reject it because we cannot divide by 0. That's a check. When you're solving radical equations, remember that if you start with x equals 2 and you square both sides and get x squared equals 4, remember that that equation actually had two solutions, 2 and negative 2, that worked for x. So these were not equivalent equations. Equivalent equations have the same solution set. These are not equivalent. This is why when you do things like square both sides of an equation, you have to check at the end. So for example, if you're solving this square root equation, we start by squaring both sides, and we get a nice polynomial equation. We end up with x squared equals 25. The square root method, we get x equals plus or minus 5. But wait a minute, because we squared both sides of an equation up here, we have to check. Plug 5 into the original equation before you got your dirty hands all over it. The 5 works out, nothing bad happens, 3 equals 3. But if you try to plug in the negative 5, wait a minute, you're trying to take the square root of negative 1, that's no good. We must reject the negative 5. I realize that root negative 1 equals root negative 1 might look good, but we don't allow that. If you try to take the square root of any negative number in a check, you're dead. You have to reject that tentative solution. The solution set is that. Only consists of the sole solution 5. In absolute value equations, well, depends on the situation. If the absolute value of x is 3, what are the only two numbers whose absolute value is x?
It's the 3.
Plus or minus 3. What are the real values whose absolute value is negative 3? Well, hold on. Absolute values are never negative. The solution set here is the empty set for this over here. So when you're solving an absolute value equation, like this over here, be prepared for a couple of cases. The absolute value of blah equals 2. That's a non-negative number, so we have two cases that can work out. If that were a negative 2, we'd be dead. Empty set. So in one case, we let x minus 1 be positive 2. In the other case, we let x minus 1 be negative 2. We solve both equations. We get 3 and negative 1, and they form our solution set. Now remember, the absolute value of x minus 1 can also be interpreted as the distance between x and 1. So we want all real values of x whose distance from 1 is 2. Well, what two numbers are 2 units away from 1 on the real number line? Here's 1. 3 is 2 units to the right. Negative 1 is 2 units to the left. And they form our solution set.
All right, and this is 5 minutes. Last piece.
Hi, everyone. Let's review section 0.12 on solving inequalities. Again, we're skimming. Read my notes. So inequalities involve symbols like these. Strict inequalities, like is less than or is greater than. Or weak inequalities, like is less than or equal to, or is greater than or equal to. Inequations involve this symbol. Now, when you're dealing with linear inequalities, you have to remember that we reverse the direction of an inequality sign if we switch sides or if we multiply or divide both sides by a negative number. So for example, if you're solving negative 3x is greater than x plus 8, well, you can subtract x from both sides. That's fine. You get negative 4x is greater than 8. But then when you divide both sides by negative 4, guess what happens? You have to flip the is greater than sign to an is less than sign. And then to write down the solution set, we want the set of all x in the reals such that x is less than -2. So the solution set consists of infinitely many real numbers. Here's the graph, all real numbers less than -2. Here's the interval form. Another way to do this is that you could subtract 8 and add 4x to both sides.
At 3x.
If you wanted a positive coefficient on x, but then when you switch sides, again, you have to flip the symbol. So in either method, you have to flip the symbol. 4x is less than -8, divide by +4, you get x is less than -2, and you end up with the same solution set. So in either method, you have to reverse that inequality symbol. When solving absolute value inequalities, it helps to think of the absolute value of x as the distance between x and 0 on the real number line. So for example, if we want all real values of x whose absolute value is less than 1, we want all values of x that are closer than 1 unit away from 0. I want all real values of x whose distance from 0 is less than 1. You can think of the absolute value of x as absolute x minus 0. Well, that's going to be this barbell here with open endpoints. To solve the absolute value of x is greater than 1, we want all real values of x that are further than 1 unit away from 0. So we want values of x that are far away from 0. We want the wings. The left wing over here and the right wing over here. We want the union of these two intervals, the wings. Numbers further away from 0 than the 1 and the -1. By the way, don't write something like this. You never put an inequality statement where you have the lesser number on the left, where you have the greater number on the left and the lesser number on the right where you have is less than symbols. Because really the values of x that satisfy this would be the empty set. Are there any real numbers greater than 1 and less than -1? No, that's garbage. So interval form is safest. Let's say you want to solve the absolute value of x minus 1 is less than 2. Well, you can think of this as u, like a substitution. If the absolute value of u is less than 2, that means that u itself has to be between -2 and +2. Add 1 to all 3 parts. We're allowed to do that. -1 is less than x, and x is less than 3. There's an implied and here. It's a compound inequality. So the solution set is the set of all real values of x strictly between -1 and 3. The graph looks like this. Technically, you're supposed to put 0, but you don't have to. In interval form, we get this. We have infinitely many solutions in here. Another way to look at it, we can think of this as the distance between x and 1. So we want all real values of x that are closer than 2 units away from 1. Here's 1. 3 is 2 units greater than 1. -1 is 2 units less than 1. We want everything in between. You can think in terms of distances. And that's all.
Wow, that was a marathon. And congratulations to all of you who stuck around. All right. Now at this time, I'll take questions. We covered a lot. I'll take questions. And of course, I'll take a few questions on Tuesday. We have some time after 1112, and a lot of questions on Thursday, next Thursday. But oh yeah, now Christopher had okay. So now, by the way, any questions in public before I stop here? All right, any questions in public? Otherwise, I'll stop the